Controlled flight into terrain describes a collision whereby an airworthy aircraft under pilot control inadvertently flies into terrain, an obstacle, or water. It is important to understand that these accidents occur with normally functioning airplanes and are preventable. American Airlines Flight 965, which crashed during descent into Cali, Colombia, is an example of a CFIT accident. The factors in this accident are representative of most dangers of CFIT, including loss of situational awareness, inadequate ATC control, communication and language barriers, misuse of automation, poor decision-making, psychological factors, mountainous terrain, night operations, and unfamiliar airport operations. Other common factors in CFIT accidents can include fatigue, spatial disorientation, and inclement weather. Despite all these factors, CFIT accidents can occur with pilots at every level of experience in any weather conditions and in mountainous or level terrain. Historically, CFIT is one of the leading causes of aircraft accidents worldwide. The number of CFIT accidents peaked in the early 1970s and has since stabilized thanks to the introduction of a number of safety improvements, including Ground Proximity Warning Systems, or GPWS, crew training on CFIT and terrain awareness, crew training specific to special use airports in mountainous terrain, and improved air traffic control altitude warning systems. Let's begin by discussing the factors that can lead to a CFIT accident. CFIT accidents are caused by the flight crew's loss of situational awareness. Situational awareness can be defined as an accurate perception by the flight crew of the factors and conditions affecting the safe operation of the aircraft. While lateral awareness is critical, more than 2/3 of all CFIT accidents are a result of altitude error or lack of vertical awareness. Knowing your position as well as minimum safe altitudes is critical to the safe completion of every flight. CFIT risk starts at the departure airport. 25% of all accidents occur during the takeoff and initial climb phases of flight. Pre-flight activities allow the flight crew a chance to become familiar with the intended flight path, which will increase situational awareness throughout the entire flight. Both pilots should cross-check the computerized flight plan against the ATC clearance and the FMS flight plan. This cross-check should use the applicable departure procedure and en route charts to ensure accuracy. The flight crew should also conduct a thorough departure briefing using all available charts to include departure procedure routing, significant terrain or obstacles along the intended departure course, and minimum safe altitudes. Airports use various types of departure procedures, or DPs, each carrying their own degree of risk. Types of departure procedures include standard instrument departures, or SIDs, and obstacle departure procedures known as ODPs. Some airports may utilize a SID to ensure terrain clearance and enhance traffic flow to and from the airport. This example shows a SID from Missoula, Montana. SIDs are mandatory if they are part of the clearance and allow the crew to depart under instrument conditions and avoid all terrain. Obstacle departure procedures can be found in the takeoff minimums pages within government NOS charts or on the backside of the airport diagram in Jepson charts. Most airports that feature terrain or obstacle risks in the area will publish an obstacle departure procedures. In lieu of a SID or specific ATC departure clearance, these procedures should be followed to ensure adequate terrain separation on takeoff. ODPs may contain departure information specific to an individual runway or procedures to be used for multiple runways. Some airports may publish charted obstacle departure procedures. These perform the same function as normal ODPs but are presented graphically similar to a CID with a clear presentation of the route and significant terrain. Air traffic control can play a crucial role in reducing CFIT accidents by providing radar coverage and low-altitude alerts. Many facilities are equipped with a minimum safe altitude warning system, or MSAWS, which provides visual and aural alarms when an aircraft descends too low while approaching an airport. The system operates in two modes. A surveillance mode provides minimum sector altitude alerts in the terminal area, and a tailored mode that monitors the airplane's altitude versus its position on final approach and provides an alert if it descends too low. Let's look at an example where an airplane descends too low during a nighttime visual approach. Approximately 12 nautical miles from the runway, the airplane is cleared for the approach. As the aircraft heads toward the airport, it starts descending below the glide path. As it continues this descent, the airplane eventually descends below the MSA. The MSAWS alerts the controller, who in turn transmits to the airplane. The flight crew initiates a go-around and avoids a potential accident. It is also important to understand how proper communications and ATC services play a role in CFIT accidents. With the growth of global aviation, the common language of English has become increasingly difficult to support. This lack of proficiency can cause confusion with ATC clearances and pilot requests, increasing the odds of an error. An additional consideration to keep in mind is that ATC is not always responsible for safe terrain clearance. In some countries, when ATC issues an off-airway clearance, the burden of terrain separation rests with the flight crew. For this reason, you should be aware of what services are provided and maintain a high level of situational awareness when operating in foreign airspace. Keep these principles in mind to reduce your risk of a communication error. Always exercise good radio communication discipline. Know your position in relation to the highest terrain and obstacles in the surrounding area. Finally, challenge or refuse any ATC instruction when it is not clearly understood, is questionable, or when you believe the clearance may lead to unsafe terrain separation. As we've discussed, it is very important to maintain vertical situational awareness. A clear understanding of the lowest safe altitude in any given flight segment is crucial. While operating in IMC conditions or at night, the flight crew must rely on en route and approach charts to determine the minimum safe altitudes. The en route charts display these altitudes in various places. While operating on an established airway, you can always descend to the minimum en route altitude, MEA, or minimum obstacle clearance altitude, MOCA, and ensure sufficient terrain separation. When not on an established airway, the off-route obstruction clearance altitude provides a minimum safe altitude in any given sector. All of these altitudes provide a minimum of 1,000 feet terrain clearance in non-mountainous areas or 2,000 feet terrain clearance in mountainous areas. Minimum altitudes and obstacles in the terminal area are displayed on approach charts. On each chart, a minimum safe altitude is depicted to provide situational awareness during an emergency or abnormal situation. These altitudes typically extend 25 nautical miles from the reference nav aid. Obstacles and spot elevations are depicted to give an indication of their proximity to terrain. Minimum altitudes on the approach course provide adequate terrain clearance. Additionally, some foreign countries also provide an emergency safe altitude, which provides terrain clearance up to 100 nautical miles. Incorrect altimeter settings have contributed to many CFIT accidents. Altimeter setting errors can result from unit confusion, metric conversions, mistaking QFE and QNH altimeter settings, or by setting the wrong value in the altimeter window. Altimeter setting units are a problem that's compounded by language barriers and non-standard phraseology. There are three basic altimeter units: inches of mercury, hectopascals, and millibars. Some areas of the world use inches of mercury while others use hectopascals. Always know which altimeter setting is being used by ATC. Additionally, in some areas of the world, meters are used as an altitude reference instead of feet. This typically requires the crew to use conversion charts or, on newer aircraft, switch the altimeter display units to meters. One additional source of confusion is QNH, QFE, and QNE settings. The QNH altimeter setting is the typical setting used when departing or arriving at an airport. It is obtained by taking the local station pressure and converting it to the equivalent pressure at sea level. However, in some parts of the world, altimeter settings are reported as QFE settings, or the actual surface pressure not corrected to sea level. Always be aware of the altimeter setting that is being reported by an airport. There have been incidents in which a QNH setting has been erroneously used as a QFE setting. In this case, the aircraft altitude will be lower than intended, resulting in a loss of separation with terrain. Complacency on the flight deck can also increase the risk of a CFIT accident. Let's look at a brief example of how complacency can affect the flight crew. On arrival into a familiar airport surrounded by elevated terrain, the crew receives a late descent clearance. Towards the end of the descent, the crew receives a GPWS warning, which is not unusual for this route of flight.
Too low, terrain. Too low, terrain.
Both crew members disregard the warning, having heard it previously on similar flights. What they do not realize is, in their haste to start the descent, they have inadvertently set the altitude selector 1,000 feet low. Steps that can be taken to reduce complacency include recognizing that familiarity of an airport can lead to complacency. Recognizing that each flight is unique and may not present the same conditions as previous flights. And always adhering to established procedures. They are designed to prevent CFIT accidents. While CFIT accidents can occur in any phase of flight, they are most likely to occur during the approach and landing phase. These accidents are most likely to occur close to the runway, between the outer marker and the runway threshold, on a relatively constant 3-degree flight path, on the center line of the final approach course, and during non-precision approaches, specifically VOR and VOR DME approaches. Non-precision approaches present some unique risks, including inaccurate or poorly designed approach procedures, various approach angles including shallow approaches, and multiple step-down altitudes. We have discussed situations that may result in CFIT and some techniques to reduce these risks. In this topic, we will discuss additional measures that can be taken to prevent CFIT accidents. One of the most important techniques for minimizing the likelihood of CFIT is to fly a stabilized approach. While each operator typically sets their own standards for a stable approach, they normally include a constant rate of descent along an approximately 3-degree flight path with stable airspeed, power, and trim. No requirement for excessive maneuvers to keep the aircraft on the lateral and vertical course, and the aircraft configured for landing. A missed approach should be executed if the aircraft is not stabilized at an altitude of 500 feet AGL. Modern autoflight systems can track altitude, heading, airspeed, and flight path with remarkable accuracy. By easing workload, they allow the pilot to concentrate on the big picture or situational awareness. Flight crews should take full advantage of the autoflight system to reduce the likelihood of CFIT accidents. As a general rule, the autopilot should be used during all approaches in IMC. And always ensure that the use of autopilot and auto throttles adheres to company procedures. In addition to the autoflight system, many newer aircraft can display terrain on the navigation or map display. This function uses GPS position data and a terrain database to display terrain and obstacles. This system should be selected on during departures and arrivals where elevated terrain may present a risk. As discussed earlier, CFIT accidents can occur when vertical situational awareness is compromised. It is essential that flight crews are aware of aircraft altitude relative to the terrain. Here are some techniques that can be used to improve altitude awareness. When approaching an airport, ascertain the applicable MSA and the MSA's reference point. These reference points change according to the actual instrument approach. Know the applicable transition altitude or flight level for the area that you are flying in. Set and confirm the altimeter setting when descending through the transition altitude. Call out any significant deviation from the assigned altitude. Include radio altitude in the instrument scan for all approaches. And when crossing the final approach fix, outer marker, or equivalent position, the PNF should cross-check the actual crossing altitude against crossing altitude on the chart. Crew callouts and coordination can also increase situational awareness and ensure both pilots are on the same page. Once the radio altimeter is active, it should be included in the instrument scan for the remainder of the approach. Any deviations from a normal approach should be communicated by the pilot flying. The rate of CFIT accidents worldwide peaked in 1973 and then began to decline steadily. This decline coincided with the requirement to install Ground Proximity Warning Systems, or GPWS, in all U.S. aircraft in 1975 and by ICAO requirement in 1979. There are two types of GPWS: the older Basic GPWS system and the newer Enhanced GPWS, or eGPWS. The basic GPWS system uses the radio altimeter and air data computers to provide a terrain warning to the flight crew. This provides adequate warning for the pilot to take action, climb the airplane, and avoid a potential CFIT accident. The newer eGPWS uses data from the aircraft's GPS and a terrain database to provide a greater safety margin. The system increases warning times and can provide improved situational awareness by providing a more comprehensive set of cautions and warnings. EGPWS can also display terrain information on the flight deck displays. A go-around should be executed when you are unsure of your current position, you are unsure of your proximity to terrain, the approach becomes unstable, or a GPWS warning occurs. Executing a go-around allows you to regain your situational awareness. If you receive a GPWS warning, the GPWS escape maneuver should be accomplished immediately.
Too low, terrain.
Failure to react immediately to GPWS warnings has contributed to several accidents. The GPWS escape maneuver can vary by aircraft and operator, but here are some guidelines. Apply maximum thrust and rotate the aircraft to the appropriate pitch attitude. Roll the wings level to ensure maximum performance. Always respect the stick shaker, and retract the speed brakes if extended.